Hi team, good afternoon everyone. Myself 𝗦𝗶𝗺𝗃𝗵, and first of all, thank you so much for taking out your precious time for joining us in this webinar today. So we are Meson Labs expert partners for Siemens and Altair, and the topic of webinar is accelerating product development with integrated flow simulation using Simcenter FloEFD. So when it comes to product development, efficiency and accuracy are something which are non-negotiables, right? So SimCenter FloEFD has revolutionized how we look at CFD by fully integrating it into the design workflow, allowing for early stage insights as well as smart decision making. So our presenter today is my colleague 𝗏𝗺𝗃𝗵𝗿, who brings extensive expertise in flow simulations. He will walk us through the core capabilities of FloEFD and how it bridges the gap between design and analysis. So in between, please feel free to drop your questions in the chat throughout the session, and we will address them at the end. So Praveen, over to you.
Thank you, Ankit. Once again, very good afternoon to everyone for taking out time for joining this webinar. So today's webinar is on the topic accelerating product development with integrated flow simulation. So here we are going to show you the solution from Simcenter, that is Simcenter FloEFD, how it bridges the gap between the design and the simulation and how it accelerates the product development. So let me go through my presentation. I am Praveen. I am application engineer for CFD solutions at Meson Labs. So as you can see in this slide, we have a control valve simulation, which is carried out using the Simcenter FloEFD. So here in today's webinar, we will show you how the FloEFD simulation is different from the traditional CFD methods that most of the companies follow, and how you can accelerate the product development with making use of the Simcenter FloEFD. So we'll also have a live demonstration after the presentation where I will take this case study of control valve simulation, and we'll see how to measure the various outputs in various formats. So we'll see in detail during the live demo. And meantime, if you have any doubts, you can put it in the chat section as well. We'll take that and we'll take it up in the end. So if we look at the graph, which tells us between the simulation purpose and the value here. So most of the companies work here in validating, in troubleshooting, and in redesigning the model again and again. But it doesn't add much value to you. So whereas instead, what if you change your methods and start working on the design itself, on your design model itself, where you can reduce the number of iterations, and then you can what if you can automate your simulation, and what if you can explore many design ideas in the initial stage itself. So that is what adds more value to you, and that is how you can improve your product development. So that is what where the Simcenter FloEFD helps you in. So with this, you can accelerate your product development. So by redesigning in the design stage itself, by automating your entire workflows, and by exploring. When I say explore, it is running the DOE kind of studies. This is what adds much value to the simulation. So yeah, in this slide, we'll discuss how traditional CFD is and how Simcenter FloEFD is, workflow is, and what is the need to democratize CFD. So if you look at this pyramid here, we have more number of design engineers who are working. When we compare with the CFD specialist, we have very few CFD experts who finally carry out the CFD simulations once they get the design. But what if we make simulation available for the designers with minimal efforts? So they can redesign number of times, and they can come up with the optimum design, and then finally the CFD engineer can perform the simulations on that. So here we are reducing the number of iterations and we are checking the possibilities of multiple designs, how best optimum design we can have in the design stage itself. And one good thing is design engineer can carry out all the simulations without having much knowledge of CFD. So that is what this graph tells you here. In traditional CFD, most of the time you're working on the CAD, whereas in FloEFD, it is CFD itself at every stage. So be it the concept stage, detailing stage, or prototyping or testing, you are working on CFD directly. Okay, so Simcenter FloEFD, how it works is, let me tell you. You have major CAD platforms, CAD softwares in the market. If you name few, they are SolidWorks, Creo, Solid Edge, and from Siemens portfolio, we have Solid Edge and NX. So once your design is ready, in traditional CFD, what happens is a design engineer will export the CAD in the required format and it is sent to the CFD team. Whereas with FloEFD, what you can do is once your design is ready, you can launch FloEFD in the background and you can just carry out the simulation then and there itself. So one major thing which we are eliminating here is CAD exports and CAD imports in the simulation environment. And next is it is within your CAD environment. So in same user interface, you are just launching the FloEFD in the background and you are carrying out the analysis, which is very quick. And it has some unique CFD technologies inbuilt, like it takes care of the intersections automatically. It captures the fluid cavity automatically. It captures the small gaps automatically, and it will place the number of required cells and or meshing. So it does all that automatically without having the, you don't have to have any CFD knowledge for that. So it makes very easy for the design people, I can say, to carry out the simulations with very minimal efforts. Just by setting few parameters, entire simulation is performed. So benefits, as I mentioned, no translation step necessary with loss of geometrical fidelity. Then and there itself, you can launch the FloEFD and carry out the analysis. So as mentioned, it supports for various CAD softwares, that is for majorly for SolidWorks, Creo, Solid Edge, and NX, and CATIA as well. So for today's demonstration, I will be using the NX, which is the CAD tool from the Simcenter portfolio, and then I will be performing the simulation with NX with FloEFD. NX integrated with FloEFD in the background. So for you, if you want to carry out any CFD simulations, first thing is you will have to have a native CAD software on which you are designing. On top of that, if you are integrating the FloEFD with that, you can perform these simulations and get your results in very quick time. So now let's discuss some of the unique enabling technologies which drives front-loading CFD. And when I say front-loading CFD, it is this approach which Simcenter FloEFD follows. Here we call it as front-loading CFD, which is different than the traditional CFD methods. So here, let us discuss different features here, what FloEFD has. First of all, embedded CAD platform. I have mentioned it as Solid Edge here, but as mentioned in the previous slide, it supports major CAD softwares. And then is the fast meshing, which is automatically generated in the background by the solver. You don't have to generate the volume mesh manually here. You just have to set the element size criteria and few meshing parameters. Meshing is automatically taken care by the solver once you hit the run button. And turbulence model is one of the very important parameter in calculating the flow parameters in CFD. So here by default, it is the K-epsilon model, which is accepted and validated for most of the applications here. So turbulence model used here is the K-epsilon. Next, the boundary layer, which again is one of the great feature of FloEFD, wherein it captures the small gaps properly and automatically. You can automate your entire simulation, and then you can carry out the what if analysis. That is, you can run the DOE kind of studies. Again, the easy to use interface. So we'll see all that in detail during the live demonstration. Okay, so let's discuss how Simcenter FloEFD adds or gives you the unique value proposition here. So as listed, it's very easy to use. It is within the same user interface that you use the native CAD for generating the models or designs. There itself, you can launch the FloEFD and start the simulation. It's very fast. When compared to the traditional CFD, it approximately reduces up to 60 to 75% of your simulation time. And accurate as well. When I say accurate, it's not solving any different things. It is same Navier-Stokes equations in the background, which is trusted by thousands of engineers and which is used for which is used in many of the commercial and traditional CFD software. And it democratizes CFD. When I say democratize CFD, it means it is bringing the CFD approach in the initial stage itself. So every design engineer can perform that CFD simulation in the initial stage. So when it comes to the CAD handling, it is very effective in terms of handling the, no matter how much complex your geometry is, it automatically captures all the geometry and intersections. And meshing, it performs the meshing based on the given parameters very fast and very accurate. And the few intelligent engineering models, I would say, because if you want to perform any CFD simulations, you need to have a knowledge of generating a proper mesh, generating proper boundary layers, capturing the thin gaps very properly. So all that is eliminated in Simcenter FloEFD since it has integrated intelligent models here. And then you can high automation, you can automate your entire workflow. So these are some of the unique value propositions from Simcenter FloEFD. So let's look at the meshing technology here. So here for meshing, it uses something called refinement levels. It is based on the refinement levels. You don't have to do the manual meshing here. So yeah, if you look at this image here, so there are a number of refinement levels, but if you go inside the small gaps, the refinement level is increased automatically by the solver. So this is used to capture accurate flow simulation or flow gradient, I would say. So here again, if you look here, as you come close to these solid boundaries, the refinement levels are automatically increased. So this is how, and even at the wall, you can see the refinement levels are it is little dense here. So that is how smartly FloEFD captures the flow gradients and the solid and fluid interaction, I would say. So another great feature is easy to use interface here. You have the wizards wherein you can quickly set up your entire simulation in just few clicks, and then you can run the simulation and you can export your reports in detail, and you can automate as well. So as discussed, yeah, the turbulence model in the background is the 𝗂𝗏 model, which is capable of solving most of the CFD applications. So here, let's look at this image, how beautifully the meshing is done in the small gaps. So as you can see here, refinement levels, it is bit large here, but since the gap here is very less, the number of refinement levels are increased automatically to capture this gradient over here. So that is how this is automatically done in the background. So number of what-if analysis you can perform. You can run the design of experiments. You can run number of simulations just by cloning the projects. That also we'll see during the live demo. So here, this is one of the important slide here, which differentiates between the Simcenter FloEFD and the traditional CFD here. So no matter which solver you are using in the traditional CFD, you will have to perform some of the few stages like pre-processing. You will have to spend much time in the pre-processing stage, then generate a mesh, then do the physics solution setup, and then run the simulation and get the results, and then do the post-processing. But in FloEFD, if you look here, required numerical knowledge is almost none here. When compared to the traditional CFD, we don't have to have any knowledge for making use of this simulation solution. User manual meshing time, none again, whereas you need quite high amount of time for the meshing in traditional CFD. Overall meshing time, CFD plus based on the user experience, it is low and high in the traditional CFD. So all the steps and all the necessary skills required for carrying out the analysis in both the platforms are listed. You can see in most of the cases, it is either low or none here in Simcenter FloEFD. And typical user profile, it is developed keeping in mind for the designers. 90% of the mechanical engineers would be able to make use of the solution and run the simulations, 10% CFD experts. But whereas in the traditional CFD, we'll see most of the users are from the master's or PhD level. We need CFD expertise to carry out the simulation in traditional CFD. So what Simcenter FloEFD can do, the listed are the various industry-wise sectors where FloEFD can benefit. In the aerospace, you can also perform the external aerodynamic analysis. You can make use of FloEFD for the automotive cases, for the HVAC, for the electronics. It is widely used in the electronic industry, I would say, for the heat transfer analysis. Okay, so these are some of the specific applications and the results carried out by the FloEFD here. So let me go through all these slides quickly, and then we'll move into the live demonstration. Flow fields here for the force aerodynamic coefficients for the external aerodynamic cases. This is again smart cells. This is at the interface of fluid and solids here. If you look at this model here, which is immersed in water, you can see the number of refinement levels, how it is increased at the wall region to capture the boundary layer effects. So this is how the meshing is done in the background. And you can see the gradient here, how properly the gradient is captured by the refinement levels. Okay, so today's demonstration, it is on the control wall. So as you can see in the slide here, this is our fluid path, which enters from this section at 10 bar, and we can give the outlet at 0 static pressure. The working fluid would be water here in our case. Then, okay, so here we'll take this model. The model with me is in the format of step file. So we'll launch FloEFD. We'll launch NX first, and then we'll launch FloEFD. We'll load this model and carry out the analysis. So I have not loaded anything. I just thought of starting it in front of you all. Just a second, it is loading. Yeah, so here I have the NX here. So This is the user interface when you launch NX. So let me just load one of the model here. I'm going to demo once. So all these formats, which you can see here, step file, IGS, Parasolid, CATIA, you can either import it here, or once you are designing the model, once your design is complete, you can just launch FloEFD in the background. So I will show you the steps here. So I'm keeping it all files. So as you can see, I'm just clicking on this step file, which is available with me, and opening it here. Converting step file. So it is doing some conversion in the background. So now it has loaded the entire model here. So this is my model. So if you want to modify anything in the design, you can do it in the native CAD platform itself here. So as you can see, there are number of parts here. So let me just show you all of them. So once your design is complete, so the way how you can launch the FloEFD in the background is go to the file here, all applications, simulation, and just click on FloEFD simulation. The moment you click on this, a separate ribbon appears here with the, as you can see, there is a separate ribbon over here that is flow analysis and all these options which are related to the simulation. So once you activate this project, all these options will be activated, and you can make use of these options for running the simulation. So before heading into the simulation, let me show you in detail how this model is. So let me take a cut section and show you. So this is my cut section here of wall. Currently it is in the closed condition. So fluid enters from this section, which is my 25 mm dia here, that is water, and it exits from this section and it passes through the narrow gaps between the plug and the solid body. So currently it is closed. So let me move this plug to some distance here. So I'm clicking on this, move. Either you can enter numbers or you can manually drag it here. So yeah, there is some gap. I have moved it 2.1 inches here. Dimensions are in the inches here. Say OK. You can convert your dimensions at any point of time. Let me just show you that. Units manager. So you can convert your dimensions. I can keep it in the metric as well here. SI units. Okay, close. So as you can see, currently there is some small opening. Fluid passes from this section. So let us see how to perform the simulation for this in the FloEFD user interface very quickly. So if I ask you a question, like how much time it would take for you to perform simulation on this model in traditional CFD? So it would be somewhere 3 to 4 hours, somewhere 1 hour for doing the pre-processing, then generating a mesh, setting up, and then once you get your final mesh, then final time depends on the running the simulation and based on your number of cores availability. But the same simulation can be performed in FloEFD analysis, FloEFD environment in just few minutes. When I say few minutes, maximum 30 minutes, 15 to 20 max, we can complete the entire simulation. So let us see how to perform the simulation for this. So now I have moved this plug here. There is an opening. So let me close this cut section. So to capture the fluid path here, I need to close this inlet and outlet surfaces. Let me quickly do that. So I'm making use of this create lids option. Click on this. So it has closed my inlet face here. So again, I want to close this outlet surface here. So again, go to create lids. Click on this planar surface. It will automatically detect the gap, I would say, and it will close that gap. Say OK. So complete my fluid cavity is almost captured. So let me show you how software captures it. So first let me save this file. So I have saved it file. Okay, so let me show you what happened to the working folder here. So if you can see this, this is my working folder where there was only this step file present. So once I loaded my model here, all these parts are automatically created by the FloEFD conversion, and all the simulation settings and everything will be saved in this .pit file, which is the assembly file here, final assembly file. Okay, so now let me show you the fluid cavity, how it is captured. So before heading into the simulation, one checklist, what you should do is check the geometry for the errors present in the model. So you can click on the check geometry here. Here, all the parts associated with your model will be listed. You can activate all these parts or deactivate all these parts if you want to include them in the simulation. Analysis type, here it is my internal. I'm checking on the internal here. So some Boolean operations, I'm clicking this preprocessor Boolean operation here to combine all these solids. So now let me hit on check button and let me see what errors it displays. So in the output, you can see status is successful, geometry is okay, no errors in the geometry. It has captured some of the fluid volume in terms of meter cube and solid volume as well. So let me show you the fluid volume by clicking on this. So I'm clicking on this show fluid volume. So you can see this is going to be my fluid cavity here. So this is automatically detected just by closing the inlet and outlet faces. So let me hide this, say OK. So my geometry is free from errors. So let me proceed ahead for the simulation here. So there is option called wizard here. By clicking on this wizard, you can quickly set up your simulation. So let me show you how you can do that. So click on the wizard here. In few options, your entire simulation is set up. So let me quickly give the project name, internal flow. Configuration, yeah, current configuration. Next. So it is asking me the units in which unit format you want to proceed. So let me say SI units only. If you want to change any units here, you can definitely change that. So currently temperature is set in the Kelvin here. You can change it to any one of this. You can keep it in the Celsius as well. So you can completely customize based on your interest. Next. So once I click next, it is asking me the various physical features here, like what kind of physics you are going to solve in this simulation. So currently it is going to be the just flow simulation. I'm keeping the fluid flow activated here. Then next, analysis type, since it is going to be my internal flow simulation, I'm going to check internal here. Geometry recognition. So here there are various options. You can select any one of these. What it does is it combines all these parts into one and then keeps the connectivity from one solid to the another. So let me keep the preprocessor Boolean here. So exclude cavities without conditions. So if this is activated, so what happens is sometimes there are multiple fluid cavities which are automatically detected by the solver. So if this is activated, only those fluid cavities on which the simulation boundary conditions are applied will be considered for the simulation, and then only that will be on only that the mesh will be generated and the solution will take place. So it is important to make a note of this, whether you want to keep this or not, but most of the time just keep it on the keep it activated, as it reduces your time and focuses on your main simulation parts. Next. So here in liquids, I want to use water. So you can make use of any one of these, or you can create a user defined material as well. So I'm going to use water as the fluid medium here. Flow type, you can mention whether this is laminar, turbulent, or laminar and turbulent. So let me keep it laminar and turbulent here. Next. So by default again, default wall thermal conditions and roughness. Let it be in default conditions. Here are some of the initial parameters to be set. So initial pressure and temperature is fine for this analysis. Then click on the finish here. So if you can see, in just few clicks, we have set up the entire simulation here. The fluid cavity is captured. The flow physics is defined in the wizard. The fluid material is defined. Initial parameters are set and everything. So if you want to modify any one of these parameters, you can just click on these general settings here, and you can modify all these options at any point of time in the simulation. Okay. So once this is done, you will see the internal flow, which I have named it as internal flow here, and the simulation tree, which is listed here. So computational domain, as you can see, this is the computational domain on which the governing equations are going to be solved, and the fluid cavity is captured here. So let me hide this. Okay, let it be. So you'll have some idea. Let me keep it activated. So now next steps are to apply the boundary conditions and then generate a mesh and then run the simulation. So to apply the boundary conditions, I'm going to the boundary conditions here, insert boundary conditions. So here I'm going to select this face here. So this is the outer surface. So I want the inner surface of this. So just click on this, select from list, and then this face. So if you see here, this is a lid and it has two faces, one outer surface and one inner surface. So I want this inner surface on which the boundary condition to be applied. So here there are various boundary condition types, flow openings. These are pressure openings and these are wall conditions. So in the flow openings, I want to keep the, as stated in this slide, let me keep the static pressure. Let me give the static pressure as some 10 bars. So I think, yeah, adding 10 would be fine here, close to. Then say OK. You can see one boundary condition is created here, that is static pressure 1. So similarly, I want the outlet condition to be defined. So I'm going to boundary conditions, right click, insert boundary conditions again. And I want the inner surface of this list. So click on the select from list and then inner surface. So this is the outlet condition. So here I want it to be, we can keep environment pressure or static pressure. So let me keep static pressure here. Okay. Static pressure. Okay, this is fine. Say OK here. So my boundary conditions are assigned, pressure 1 and pressure 2. Now, next step is to define the mesh. So let me show you how you can generate a mesh here. So it is in simple clicks. I'm clicking on the global mesh here. So there are two types in which you can create a mesh. Either you can create it manually or you can create automatic. So you can see the scale, which is ranging from 1 to 7. This is nothing but the refinement levels. So if I'm increasing this, so you're making it very fine mesh. So you have scale ranging from 1 to 7. 7 is the maximum refinement level available here. So let me click on this show basic mesh. So you can see when I increase the refinement level, it is becoming very fine mesh and all these refinement levels are created. So for this analysis, 4 is sufficient. And one thing that you should take care of here is small gaps between your model. So here in my model, I want to keep you can activate here minimum gap size. So I want to keep minimum gap size here to be detected as 1 mm. So let me change that. So this is it. Once you set these parameters, the mesh settings are done. So no more settings required. Just save the file here. Go to the run, or you can go to the calculation control options as well, and then make some modifications if you want to. You can also run this in steady or transient state. So currently it is the steady state here. So here, once this is done, okay, one important thing I forgot, that is the goals here. Goals are nothing but your results. So insert surface goals. So here you can see the number of results in various formats, like various parameters like static pressure, total pressure, dynamic pressure, velocities. So all these results you can request before running the simulation itself. So how you can do is, I want my results on the inlet surface and outlet surface. So I'm going to click on the static pressure one here. So I want to measure the velocity on that surface. So I'm going to click average velocity here. As you can see, there are different columns, that is minimum, average, maximum, and bulk average. So also you have one more column wherein you are using that result request for convergence, use for convergence. So this velocity request on the inlet surface will be used for convergence as well. So the simulation will continue until that result gets converged. So that is what it means in short. So I want velocity. I am saying OK here. I want a few more results. So I'm going to activate that. So I want velocity in the outlet as well, static pressure 2, and average velocity there. Say OK. Again, I want to add few more results. Temperature, no. Mass flow rate, yeah. Let me click this, static pressure 1 and mass flow rate. Say OK. So once you have set the goals, save the file, then run the simulation. So I'm just clicking on this run button, and it will ask you some of the options here. Run at this computer. If you have any other computer with number of high number of cores, you can add that here. Number of cores, I'm going to say 6 cores here, and then finally run it. So a separate window is launched by the FloEFD, as you can see here. So in this window, so let me align it properly. So in the bottom, you can see the status here, calculation. So here it is showing you the list of goals that you have requested. I have requested 2 velocity results on inlet and outlet, and at one surface I have requested the mass flow rate. So let me align it properly, tile vertically. And then it is some information here with respect to the simulation. The number of cells, number of total cells, and CPU time, everything related to the simulation is given here. Then there is a log file. Then here, there are some of the result files here. So as you can see this curve, the number of iterations are 25 here. So you can, okay, let me show you this insert goals plot. So I want mass flow rate, or I want all of this. No, let me keep only this, say okay. Okay, this is the same graph here. I want mass flow rate graph. So your simulation will continue until this result gets converged. So you can see this graph, it is stabilizing now. As you can see here, there are 2 lines. And you can see the simulation speed here, how fast this is. It will take another few seconds or few minutes, 1 or 2 minutes. So till then, let me show you the user interface here. So if you look at these various ribbons here, these are with respect to the native CAD platform. That is, be it your whatever the CAD software that you're using. And once you launch your FloEFD software, another ribbon gets added to this, that is flow analysis ribbon. Okay. Okay. Now this simulation is complete. So if you see this window here in the bottom, you can see solver is finished. So as you can see, there are this is properly stabilized. So there is no meaning in running or continuing the simulation anymore. So once your simulation is complete, you can post process the result in the same user interface. So that is one more beauty of this software. So let me show you the results here. So first, let me start with the cut plots, insert cut plots. So I'm going to have the pressure counter. So I'm going to select this. Okay, select a plane here, XY plane, and then pressure counter on that. Say okay. So you can see this is my pressure counter. So let me activate this. Let me take a cut section of this. So yeah, now you should be able to see it properly. So this is my pressure contour. So if you want to change it to any other result, you can do that. So you can simply change from these options available here. So let me take velocity now. So you can see the velocity here. If you want to activate the vectors, you can activate the vectors also. I'm going to say OK. So you can see the vectors as well. So you can see how beautifully it has captured the gradient between these small gaps here. Okay, so now let me take the flow trajectories, which is again a good option to visualize your results. So let me activate this, remove this cut section, and then okay, select this surface here, which is my inlet, and I want some 50 seeds on that. I want the dynamic trajectories. I want result in velocity. Yes. I'm saying preview. You can activate this preview also. It will show you the results. Say OK. So let me reduce this transparency. Okay. So now, okay, let me hide this cut plot also. You can see the, okay, let me hide this domain. Now you can see properly. Or let me increase that. Okay, this is fine. So you can see the vectors or flow trajectories. If you want any animation of this, you can definitely do that. So I'm going to click on the flow trajectories and say play. So it will tell you the flow trajectory of fluid. So you can see how beautifully it is showing you the flow path. Yeah. So you can properly visualize your results here. So this entire simulation from design to setup and running, it took about 10 to 15 minutes only. Okay, let me stop this. So once your simulation is complete, once your results are, once you extract the result, you can also export it to the result formats. Or if you want to perform any other new simulation by varying this plug, so in just few clicks, let me show you how you can do that very quickly. So let me save this. So say you want to run another simulation with by varying this plug movement here, plug distance here. So simply you just have to click on this, clone the project. So another project, you can name it here, internal flow 2, say OK. So it will make copy of this entire simulation setup and another project will be loaded. So now all these options are with respect to the second project. So if I want to move this plug again by some distance, so I'm just clicking on this. So let me just move it by another few distance. Okay. Move. Okay. So this is enough. So again, if you want to perform the simulation for this, you don't have to go through the all setup from the beginning. Just hit on the run button. Simulation for this setup will continue. So this is how you can make number of projects. You can clone your projects and you can modify the boundary conditions or your model, or then you can run the simulation. So this is one way of quickly doing the CFD simulations using the FloEFD solution and coming up with the optimized design, I would say. So here we are completely eliminating the CAD exports. There is no need of exporting the CAD to the required format and then sending it to the design, sending it to the CFD team. So it completely eliminates that process here. Once your design is complete, you just have to launch FloEFD in the background and start simulation. And even the simulation setup doesn't take much time. Just in few clicks, you can set up your simulation and then you can run your simulation. And also once your simulation is complete, you don't have to go back and start fresh another simulation by varying the geometry parameters. In the same user interface, you can clone your projects the way I have shown you here, and you can modify boundary conditions or model geometry, and then just hit on the run button and simulation will continue for the another setup. So this is how you can accelerate your product development with help of FloEFD.